Okay, so in this video we're going to take a look at a past practical paper from the AQA ICES. So this one was all about how the rate of cooling is affected by the initial temperature of a liquid. So that's the experiment that was done before this, but now we're going to look at some theory questions, but still using the same practical skills. So we're going to be looking at Newton's law of cooling, which states that the rate of temperature change is directly proportional to the temperature difference between a body and its surroundings, which is given by this equation here. So we're going to be looking at it modeled in its exponential form, which you can see on the right-hand side there. So we've done another experiment. We've collected some data. We've got the time and the temperature. And now what we're going to work out is essentially what each of these properties are here. Assuming that the room temperature is at 19 degrees C. So phi is the temperature difference, and then we're going to take log phi, which we're going to plot on a graph. Okay, so first of all, explain why a data logger with a temperature sensor justifies 3 sig figure precision, whereas a stop clock and a stopwatch with a thermometer would not. So the key here is that a data logger can take measurements simultaneously. So for every time, it will take a reading of temperature straight away. Whereas if you're using a thermometer and stop clock, you've got to look at one and then look at the other. There's always going to be a delay, so you can't justify that level of precision. Okay, so what we're going to do is complete the table that we saw earlier. So here is the table. So for the first column, essentially, we're subtracting room temperature, so fairly straightforward, but staying consistent with 1 decimal place. And then when we calculate the logs, we're giving each of them to 3 significant figures. The first number in a log value is not significant. It's called a placeholder. So essentially, we're giving all of these to 3 significant figures because all of the temperature differences were 3 significant figures. Okay, so that's our data. So complete the graph of the cooling data on the next page by plotting the remaining points and drawing a straight line of best fit. So that should look something like this. Your points should be marked with an X, and for the best fit line, there should be roughly the same number of points above and below the line, which you can see I've got there. I've got 2 below the line at the bottom, and then 1/2 above the line. Okay, so explain how the graph supports the formula. The temperature difference is equal to the initial temperature difference times the exponential of minus kT. So first of all, let's rearrange the equation into a form that matches with the graph. So if we take log of both sides and then use our log rules to separate out that, we get this expression. And so that equation predicts the graph of log of temperature difference against time should be a straight line with a negative gradient and a non-zero y-intercept, which is exactly what the graph we've plotted shows. So it does support it. Okay, so then we want to determine the gradient of the straight line. So I'm going to use as much as possible of the graph. So I'm going to use where it crosses the y-axis and where it crosses the x-axis. Read off the coordinates at each of those points as precisely as you can. And then you calculate the gradient like this. And my gradient comes out as minus 0.0763. And we'd expect to get a negative value because it's sloping down. Okay, so that's our gradient of our line. Now we want to find the value of k and state its unit. So remember from the equation we had before, k is minus the gradient, so k is going to be 0.0763. The y-axis has no unit because it's a log. The x-axis is a second, so it's going to have the unit of seconds to the -1 or per second. So we're now going to use the graph to find the initial temperature difference. So the y-intercept is log of the initial temperature difference. So if we take the exponential of that, that gives us the actual temperature difference of 32 degrees C. And if using the equation from earlier, if we know the initial temperature difference, we've just found K, we can find the initial rate of decrease of temperature in degrees centigrade per second. And then we can essentially go through the same process at 60 degrees. You can read off the value of log of temperature difference, calculate the temperature difference, then multiply it by K to get the rate is 0.15 degrees Celsius per second. And we can see that the rate has decreased, so that makes sense. Okay, so the results from this experiment do seem to support Newton's law, suggest ways in which the same apparatus could be used to test a wider validity of Newton's law of cooling. So in this experiment, we've only investigated it for a small temperature range over a short period of time. So to make sure that Newton's law is widely applicable, we need to make sure it works over bigger temperature differences and also over much longer periods of time. So that's how you'd extend to test in a wider context. Okay, so one major physical factor contributing to heat loss from a heated swimming pool is evaporation from the water surface. This can be virtually eliminated while the pool is not in use by positioning a floating cover over the whole pool surface. Describe an experiment based on the apparatus used in stage 1 to investigate how heat loss by evaporation varies with the initial temperature of the water. So just to fill in the gaps here, so as I said earlier, the first experiment was investigating how initial temperature affects the rate of heat loss. So they had polystyrene cups and some hot water and a thermometer. That's all the equipment they had. So in terms of investigating this particular aspect, what we'd need is 2 identical polystyrene cups of water. And what we'd do is you had one with a cover and one without, because that's how we compare. And we're going to use the same volume of water in each cup in each test. So we're going to keep that the same. So we're going to start at 80 degrees. So we'd pour it simultaneously into both cups and record the temperature change over a period of 5 minutes using a thermometer. Okay, so that. Then we do the same thing at 70 degrees, 60 degrees, because we want to know that the conclusion we draw is valid over a big temperature range. But we're still using the same volume and the same 5-minute period of time. And then finally, what we do is we plot temperature change against the starting temperature, and that would allow us to compare how the covered cup compares to the uncovered cup to see the effect at all the different temperatures the water might be at in the swimming pool. And that concludes going through this practical exam.